This presentation will have two topics. One will show how to use Excel's Analysis ToolPak Add-In, and especially we'll be interested in the regression. And the second topic will be polynomial fits of data. Let us first review what we can get without the add-in. So here we have some XY data, some independent variables, which we'll call X, and they're in column A, and some dependent variables, which are in column, which we'll call the Y's, that are in column B. We've highlighted them. We've gone to the menu and clicked on Insert and chose a scatter chart. And then with the chart highlighted, we've gone to Chart Design at the top middle, and then gone over to the left top and clicked on Quick Menu, and chose Layout number 9 from the drop-down list. And we've edited various labels. And that gave us this XY scatter plot shown. To pursue this regression analysis further, we want the add-in. To do that, we will go to File on the menu, and then in the slide out bar that opens up, choose at the bottom Options. In the resulting Options dialog box on the left, we will click on Add-ins, and then from the list choose Analysis ToolPak, and then click the button Go. Be sure not to click OK, but to click Go. This opens a second dialog box, the Add-ins dialog box, where we are checking off Analysis ToolPak and then clicking OK. If we have succeeded in bringing in the add-in, it will appear after we click on the menu, middle top, Data, and then go over to the right and click on Data Analysis. If we didn't bring in the add-in, you won't see Data Analysis. And again, for me at least, the common mistake was in that first dialog box to click OK when one should click Go. In this presentation, we'll be interested in the regression features. So again, on the menu, top, middle, click on Data, then find on the right Data Analysis. And when you click on that, that brings up the Data Analysis dialog box. Scroll down and find Regression, then click OK. In the text box labeled Input Y Range, you can type the range, B1:B7, or what I did was left the dialog box and went over to the spreadsheet and dragged from B1 to B7. Because I included B1, which was the label, I have checked the labels checkbox in the regression dialog box. And be careful, when you're making the XY scatter plot, it wants X's to come before Y's, but in the regression analysis, it is asking for the Y's first. Using a similar method, we can fill in the input X range text box. Just to be consistent, if you used a label for the Y's, use a label for the X and make sure that the same number of data points appears in each. If there is a different number of data points, that will stop the analysis dead in its tracks. The regression will be a fit to a straight line. More on that later. In the middle area, we decide where the regression analysis output will go. The default is a new worksheet, and I have stuck with that choice. And then below there is a decision about residuals. So I decided then I would check residuals and residual plots, and we will see that effect on that new spreadsheet. So let's start with the basics. We ask the regression output to be put on a new sheet, and there it is, sheet 3, and we are on sheet 3. And then we recover the basics that we saw in the XY scatter graph. We have the R² value and the slope and intercept. They're calling the intercept. They're calling the slope the atomic radius. That was the label name of the X value, and they're calling it a coefficient. So the coefficient of the linear term is the slope. The purpose of the add-in is to go beyond what was provided by the XY scatter graph and its trend line. The trend line was to a straight line and provided an intercept and slope. The regression analysis here goes beyond that. One way in which it goes beyond that is to provide a range of values for the slope and a range of values for the intercept. For instance, the intercept the best intercept was minus 3.401. But we see here a possible range of intercepts from minus 0.7822 to a positive 1.020. And similarly, it gives us a best slope and a range of possible slopes. One of the quantities given in the regression analysis is the p-value. The main thing you should know about the p-value is that you want it to be small. How small? Well, different people will have different standards, but a common one is 5% or 0.05. The p-value is tied up with what's called a hypothesis and a null hypothesis. We're using a linear model. That really consists of two hypotheses. There's a slope and an intercept in a linear model, and so each thing is considered a hypothesis. We are hypothesizing that there's a slope. The null hypothesis, the opposite, would be that there is no slope or zero slope. The nice thing about p-value, we had an indicator r squared of if something was a good fit or not, but it was sort of for the whole thing, whereas the p-values allow us to sort of separate the intercept and slope and ask individually if we sort of trust them if they are good. And so when we look at the intercept and atomic radius, the slope values for the p-values, we see that the slope one is much smaller and more trustworthy than is the intercept for this data. We checked off residual and residual plot in the dialog box, and so here are the residuals we requested. Recall that the fit allows us to make a prediction, and a residual is the difference, subtraction, between a data value of y and a predicted value of y. You might recall, moreover, that it was the sum of the squares of the residuals that were minimized and that is what we used as the criterion for picking the best slope and the best intercept, the so-called least squares fit. The residuals are y's, and here we see a plot of the residual y's versus the corresponding x's, giving us the so-called residual plot. The original function that we fit to was a straight line, and what a residual plot might tell you is whether that function choice, in this case a straight line, was the best one. Residuals are going to have the property that some are positive and some are negative, but what you're looking for in a residual plot is possible a pattern. And in fact, in the picture that we see here, we see one of the classic residual patterns, that there are groupings of positive residuals, negative residuals, and then more positives. If the straight line were a best choice for the function, it would be a random scattering of residuals. But here we see a pattern suggesting maybe another function is in order. Here we return to the original XY scatter graph and right-click on the trendline and choose Format Trendline, bringing out the Format Trendline panel. This allows us to change the function to which we're fitting. So in the upper left, we have linear, in the upper right, exponential, in the lower left, power, and in the lower right, polynomial. And this allows us to make some comparisons. We have in previous presentations discussed the linear, the power, and the exponential forms, but this is our first time for a polynomial, or in particular here a quadratic. So let's look at some of its features. First, the dimensional analysis. We have the form y equals ax squared plus bx plus c, where x is the independent variable, y the dependent variable, and a, b, and c parameters. Y will have some unit and x will have some unit. In the particular example we're considering, y had the unit of density and x the unit of length. To keep these units what they should be, the parameter a must have units of y over x squared, or in our example in this case, density over length squared. The b must have units, y units over x units, or density over length. And c must have the units of y, density. In the linear model, the form y equals mx plus b, the slope m, is a rate of change. It tells us how much the y variable changes when we change the x variable by 1. If we want to go beyond the straight line, as we do here in the quadratic, then the slope changes. So our rate of change is changing. Or we have an acceleration or perhaps a deceleration, if you will. We have fit our example data to 4 different functional forms: a straight line, an exponential, a power, and a polynomial of order 2, also known as a quadratic. And each had its r-squared value, which should allow us to compare them and see which fit is better. But we want to point out here that this is sort of not a fair comparison. And I'm discussing here the number of parameters, but you might see in other discussions of this concept the idea of degrees of freedom. So the polynomial, let's compare the polynomial to the line. It's always going to fit better. It has the line contained in it, and then it has an additional fitting parameter, allowing it more wiggle room to come closer to all the points. And why stop there? Excel allows you to go to order 2, 3, 4, 5, 6. What you have to be careful with here is the concept known as overfitting, that you're over-concerned with getting very close to all the points may ruin any predictive power of your functional form. We return here to the output of our regression analysis. We see under r squared a quantity known as adjusted r squared. Adjusted r squared attempts to modify r squared by adding a penalty for having more fit parameters. Thus, it's trying to level the playing field and allow us to compare functional forms which have a different number of fitting parameters. One drawback is that it sort of eliminates the simple interpretation of r squared as a fraction of data accurately described by the model. So you can use that interpretation for r squared, but not for adjusted r squared. The add-in regression analysis assumes that we're fitting to a straight line. If we want to use the add-in regression analysis for a quadratic, we are responsible for creating the square terms ourselves. So we see that we have inserted a column B, and in that B we have calculated the squared A terms, and now we're ready to proceed. So on the menu, top middle, we go to Data, and then over on the right, Data Analysis. Choose Regression from the drop-down list and click OK. The Y input range, the Y variables, the dependent variables, are now in column C, and the independent variables, both x and x squared, are in columns A and B. So for the input x range, we take the range from A1 to B7, which includes both the x and the x squared choices. And so here we're comparing the linear and quadratic regression outputs. We see that as expected, the quadratic fit had a better r squared, but it also has a better adjusted r squared. Recall that the add-in regression analysis, in addition to giving us the best fit parameters, the intercept, the linear term, and the quadratic term, gives us p-values for each. Remember that p-values should be small, and a standard rule of thumb is that they should be less than 0.05. And here we see only the quadratic term passing that test. Again, the add-in regression analysis tool is set up for straight lines, but we can get it to do a power law analysis if we remember the trick that a power law fit is a straight line fit after we've taken the logarithms of the x data and the y data. And so here we're setting up to do that. We've inserted a column B and are doing the calculation of the natural log ln of the data from A, and we've performed a similar calculation of the natural log of the C data and put that in column D. If we wanted to do an exponential fit, we would just do one of these. We would just have to do the log of the y's. So on the menu in the middle, we click on Data, then we click on Data Analysis over on the right. Choose Regression from the drop-down list and click OK. In the dialog box, the y's, the dependent variables, are after taking the logarithm, are in column D. And the x's, the independent variables, again after taking the log, are in column B. Here we see the output of the power law regression analysis and compare it to the power law fit in the XY scatter chart. We see that it gives us the r squared and the power quite easily. The coefficients are related, but in a more complicated way. the adjusted R² is not as good as the polynomial fit. On the other hand, the power law fit has much better p-values than did the polynomial, suggesting that both parameters here meet the less than 0.05 criterion. So have we answered some definitive question about the dependence of density on the atomic radius for Nobel gases? Not entirely, but that was not really our purpose. Our purpose here was to see what Excel could do, what this add-in regression analysis was capable of, how to interpret some of these things, R², adjusted R², p-values, residuals, residual plots, and I hope I've shown you some of the power of Excel.